come up with a version of what we would call equations of motion on the space of S matrices, because we don't have a Lagrangian, so you require these ideas. Also, at a technical level, we will require better understanding of the numerics, because these numerics are very slow, so a better understanding means something that I can do on a laptop. And that is one challenge that I faced while working on this project, because this was done during the lockdown period. And because I happen to belong to an institute, the Indian Institute of Science, which is a giant elephant, poking it has no effect on it. So basically, they are installing a new software on any computer in the Indian Institute of Science is very difficult. So thankfully, I appealed to the ICTS folks. The ICTS folks very graciously they helped me out. Otherwise, this project would have been impossible to carry out. But we really require numerics which I can do on a laptop, because if everybody has to play, then it has to be a fair playing ground. It cannot be that you need to belong to a premier institute to be able to do these things. So we do require to have version 2 of the numerics, because right now the numerics take a lot of time, it takes a lot of resources. But we can be optimistic that what happened in the 3D Ising model for the conformal bootstrap, one can actually do precision phenomenology with the standard model bootstrap. So what happened in the 3D Ising model bootstrap was that you were able to see that the 3D Ising model was located in near some special features. So I focused on some special features in the space of allowed S matrices. The 3D Ising model happens to sit near one of these special features. You can zoom into this special feature and actually you can extract spectrum. You can extract operator product expansion coefficients. And then you can go and match them up with either Monte Carlo techniques or the epsilon expansion, and see whether which one has less error bars. So these things you can do. So you can do phenomenology with the conformal bootstrap. So and of course I was trained as a string theorist. Sunil gave a wonderful talk explaining that string theorists need to actually justify their existence more to the physics community. And so one way that we can probably find justification for existence is to see whether there is any signature of string theory from this bottom-up approach. We are not assuming anything. We are not assuming ADS-CFT. We are not assuming the fact that there's a world tree description. We are just using S matrix bootstrap unitarity. So these principles may actually point us in the direction whether there is a string description of these things. So in the last 4 or 5 minutes, let me actually talk about the grinder code. So there are these. So on one hand, these old ideas may be surprising that okay, these ideas were pursued in the 1960s, maybe in the 1970s. They have been beaten to death. What can these things possibly teach us in 2022? So you probably can feel that okay, maybe it will give us some new mathematical insights or maybe a different perspective. And indeed it turns out to be that, because the crossing symmetric dispersion relation tied in with these S matrix bootstrap program leads to a very surprising connection with an area of mathematics called norm theory. And this is something that wouldn't have been anticipated in the 1970s for a couple of reasons. So for one, people working on the dispersion relation program or working on this old S matrix theory approach were largely an ignored community. I don't think they got any encouragement from the very active quantum field theory community to pursue their program. And for two, they wouldn't have been looking at these connections because some of the connections, some of the theorems that are needed hadn't been proved. So one theorem, for example, that we need in making such connections is what is called the Bieberbach conjecture. The Bieberbach conjecture was made in 1916, but was proven only in 1985. So people working in the 1970s wouldn't have known about or wouldn't have used that technology. So the question that we can try to address is that I showed you a space of allowed S matrices and there was something interesting happening on the boundaries. So can we quantify the boundary more precisely using mathematics. So for example, can we write down an equation for the boundary? Okay, so that's a mathematical question, and you can go and figure out whether you can answer this or not. The boundary of this allowed theory space, I can explain in more detail or more precisely later on during lunch, is actually related to knot polynomials. And these are again knot polynomials for people studying knot polynomials from the 1920s. There was a period of lull over maybe around 60 years till the Jones polynomial came about. Then Wheaton wrote his famous paper on quantum field theory in the Jones polynomial. So it's a fascinating connection that these knot polynomials show up in this most basic 2-to-2 scattering that one learns in a first course in quantum field theory. So this boundary curve, so this is the last slide that I have. So these dots here are data that I have from the S-matrix bootstrap program. On the y-axis, I'm plotting some Taylor expansion coefficient of the scattering amplitude. So the precise detail is not important. It's one of the leading Taylor expansion coefficients, which is also called a Wilson coefficient. So I'm plotting a function that involves the Taylor expansion coefficient. This is the S-matrix bootstrap data. So what I've done is I've maximized the Taylor expansion coefficient from 200 set of S-matrices that satisfy the unitarity constraint. The blue curve here is derived analytically in terms of knot polynomials. As you can see, the S-matrix bootstrap data and the blue boundary curve here agree remarkably well. So in this very precise sense, the space of allowed theories is bounded by some knot polynomial. In mathematical parlance, these are called Alexander polynomials. And this is something that was recently discussed in this paper since a couple of weeks back. This is something that I want to pursue more actively over the whatever the next few years, because I believe that there is a very interesting connection to be unearthed in terms of this ancient mathematics. Which one? Yeah, so these dots are data from the S-matrix bootstrap. This red curve is phi cube theory, literally just plain simple phi cube theory. And the black curve here is phi 4 theory, 1 at 1. Okay, so it's time to officially wish my uncle for his 75th birthday, which was 2 years back, but maybe we pretend that we built a wormhole and time travel backward. Very happy birthday and thanks for all the inspiration. May you have many more.
Thank you very much, Maninder. Talks open for comments, questions. Yeah, Pato.
Excellent talk, and very nice recollections of Vikash's face expressions. Really had fun looking at them. Now, I have two questions. First is about this relative entropy. Now, you have chosen an entropy which is just a difference of two von Neumann entropies, but you could have had many other definitions of relative entropy. And I'm wondering whether all of them would place the chiral coefficient theory point within the boundary. Is there a proof?
No, I don't know. So it's kind of a difference of two von Neumann entropies. So it's kind of a difference of two von Neumann entropies. So you see, it's rho 1 log rho 1 and rho 1 log rho 2.
Right. So it's not exactly the difference.
Exactly the difference. This is one way of distinguishing two density matrices. This is not the only way. You're absolutely right. There could be other measures.
Right.
It's a good question. We have a lot of data, and we would potentially explore which one.
Other definitions. Like you could take a Rennie kind of generalization.
Yes, exactly. We looked at the Rennie generalization in our paper, and there wasn't too much difference between what this was suggesting.
So the point didn't shift too far.
Yes.
Great. That's very good because that's a robustness of the location in the angular zero plane.
Yes. This is Blanco, in fact, your colleague.
Okay, my second point was more about this grand program that you have. It's really interesting, especially because I have a certain interest, an abiding interest in Chern-Simons theory. And of course, you know that not invariants and
Yes.
related to Chern-Simons series.
Yes.
And on the other hand, Chern-Simons series show up in the quantum gravity
Right.
as the boundary description of black holes. So I was wondering whether there could be some connection to this. Wonderful. I think we should go ahead and
Yeah, that could be. I mean, so here in the Jones polynomial study, the not polynomial parameter
Right.
was exponential of 2 pi over k plus 2. So k was the Chern-Simons level
That's
number.
right, that's right.
So that is discrete. So you have a discrete set of not polynomial parameters. So here the not polynomial parameters are somewhat a little bit more natural because it is in terms of the energy variable.
Right.
It is literally the energy variable that you integrate in the dispersion relation.
Yes.
And a very interesting thing that happens, I don't know the relevance of this, is that when you go to very high energy, the not polynomials actually become degenerate. And they degenerate to the unknown.
I see.
And the unknown looks like this.
So there's a topological transition.
Yes, but you know, because you are treated as a string case, when I do this,
It's close to me. Yeah. Yes.
Okay.
Excellent. Thank you very much.
If there are,
Brenda,
yes.
what joke did you tell your uncle to elicit that laughter?
He doesn't laugh like that with you guys, is it?
No, because most of the time he was like the previous picture.
That's true.
expecting something rather sensitive because he just walked out before people answer. Okay, if there are no other questions, let's thank all the four speakers and the management for their and wonder, we are more or less on time. So, let's break for lunch. We come back according to the schedule at 3 o'clock.